Okay. All right. Welcome back, everybody. I hope you all enjoyed a nice coffee or tea. So this is the first contributed talk session of today, and we're joined by three juggernauts of our field, with Adrian Seyboldt, Paul Berkner, and Charles Margossian. And so I'm David. I'm in Aki's group in Aalto, and I just want to remind you we have around 20 minutes. We can see how much time you want to allocate for discussions, but hopefully 5 minutes or so. We'll try that exactly. And I just want to highlight two things that I've been told just now. So some of you were mentioning the lights are a bit off-putting, that they're always on. Force majeure happened, so apparently there was a storm, and so the way how you can adjust the lights hasn't been fixed yet, so that's just going to stay how it is for right now. And the other thing is that when we do the Q&As, the talks and the Q&As will be recorded and later put on YouTube. So if you don't want your contribution, your question to be recorded, then rather please just talk to them after the lecture or the talk. And without further ado, I'll hand it over to you, Adrian, on mass matrix adaptation to variational inference.
Okay. Hello, everybody. It's nice to be here again. I guess I got a pretty nice spot directly after the first keynote. I'll try my best to do it justice. I work on NumPy, a sampling library for Stan and PyMC. By now, it's the default in PyMC, and it also got an R interface, pretty new now. So if you're an R user, you can use it there as well. It's got a nice paper. Written with Elliot and Bob, who are both here as well. So if you want to look at that a little bit. The talk is more for kind of the sampler development crowd right now, I guess. 2 years ago, I tried to do it more kind of the NumPy introduction for practitioners. I do have 2 items in here that I think quite important for, or useful, I hope, for people who just do the modeling. And the first one is that the Fisher divergence is a really useful diagnostic. It's just one number that tells you or summarizes in some way how difficult a posterior is for the sampler, and it gets broken up in which variable contributes how much to that difficulty. So you can ask which variables are responsible for the sampler's trouble. And it's become my go-to thing to look at if I want to find where in a model trouble is. It doesn't help you to know what you want to do about it, but at least you can tell where the problem is. And the second one is that low-rank adaptation in NumPy works quite well by now. Wasn't really the case 2 years ago, so if you want to give that a try, that's also nice. Gives a median speed up of 4x on posterior dB, and often quite a bit more, and sometimes less. So normalizing flow adaptation is something that's also been in NumPy for quite a while, but it's been experimental, and it still is experimental. That's not really because it's not working. It actually works somewhat, it works well on some models, not so well on others. And the main reason it's experimental is that it's more of a research project than one simple method. So you can combine it and can kind of pick and choose different things you want to do, and I think it can get much better than it actually is right now. So kind of the topic of the talk is let's actually fix variational inference, because I think kind of the standard way of doing it doesn't really work, but hopefully this does work. So the main idea of this is to combine the 2 big inference algorithms that we have. So we have variational inference, which is approximate, so it doesn't give you actual posterior draws, but it can be really flexible depending on the details you choose there. So it can deal with difficult posteriors. And we have Hamiltonian MCMC and other MCMC methods on the other side that are exact in some sense. So they actually give you posterior draws if they work, but they don't work always, and they can be pretty inefficient as well. So Mike Hoffman published a paper several years ago that tried to kind of combine those 2 methods and say, okay, why not run variational inference first as a kind of preconditioning step, transform the posterior such that it gets easier with what we learned in variational inference, and then run the Hamiltonian Markov chain Monte Carlo on the residual of that. That was neutralizing bad geometry, and I hope he wouldn't be mad if I say that it doesn't really work all that well in practice. But hopefully we can fix that. So let's start with variational inference in general. So I see that variational inference thing relatively loosely. So we just fit probability distributions with known density to our posterior. That's basically what I think of as variational inference. So we need to do three things, and I think that's pretty much, we always need to do those three things independent of what we want to do exactly. We need to choose a family of approximations. We need to somehow measure how good our approximation is, and then we need to somehow minimize that distance, so we want to get a better fit. In the following, I'll always assume, that's not always the case, but I'll always assume that our family is generated by transforming a normal distribution. So we take a standard normal distribution and we transform it to generate our approximation family. So the F has kind of an index that has hyperparameters, how you transform those. Then the most popular version of ADVI is just mean field ADVI, so the transformation family is just element-wise affine, so you have just a scaling factor and a shift. So the Q are just normal distributions with a diagonal covariance matrix. The distance measure that we typically use is the KL divergence from Q to P, and we just sample our standard normal distribution, we transform it, we compute the KL divergence or approximation up to a constant of it, and minimize that with Adam. In the following, we'll kind of make three changes to that algorithm, kind of one after the other, and different things will fall out. So the first change is the KL divergence, so Y from Q to P and not from P to Q. So the KL divergence is not symmetric, we can do it both ways. The reverse KL divergence is what we typically use in variational inference. We just get, so that's from Q to P, so we get draws from our standard normal distribution, we transform that and match that to our posterior. So it's asking the question, are the log P functions similar at samples of our approximation? While the forward KL divergence from P to Q, there we get draws from our posterior distribution and ask, do they approximate each other at draws from the posterior distribution? So a simple example, if we have a little banana shape, the reverse KL divergence minimum for mean field ADVI will look something like this. And the green dots are the draws from our approximation. So we really focus on one little part of our of the actual posterior. This is where we focus on kind of, if we do this two-step approach, first running variational inference and then MCMC, all our focus is on a little part of the posterior, and kind of the interesting part, the long tails, we just completely ignore those. As long as our family is too small. If the family gets smaller, it will cover it eventually, but not directly. While kind of the reverse, if we use the forward KL divergence, or the other way around, we take draws from the true posterior and we approximate that. So we get more of a global view, and that's, I would say, what we want if we want to precondition MCMC, because Hamiltonian, the Markov chain will run at the full posterior eventually, hopefully, if it works. So we really care that they match at the posterior. We don't really care if they match at the proposal. So that's the first change we make. We just turn that around and do it the other way around. That has an unfortunate consequence. We need draws of P, so we don't kind of, in the other way around, we could just draw from a standard normal, that is easy. Now we need draws from our posterior, that is hard. But luckily we have a method for that. We get P, our draws from the posterior, with MCMC. So we start with MCMC, run that for a while, with a transformed posterior at the beginning of the transformation is just the identity. We minimize the KL divergence, and we update the transformation, and then we repeat that. We just run through that. Now we've got a fancy new algorithm and before you publish a paper, maybe you should notice that that is exactly what Stan has been doing all along. So mass matrix adaptation really is just variational inference, just with the KL divergence the other way around. Now the second change. The KL divergence doesn't care about smoothness of our approximation at all. So here are two pairs of distributions, kind of on the left. It's the left for you as well. We have kind of the true, let's say the posterior in black, and an approximation in red, the zigzaggy thing. The KL divergence will look at this and say, yeah, it looks like a really nice fit. As good as the fit on the right. Because, well, the two functions are relatively close. But HMC, if we give a jagged thing like that to HMC, it will not be happy at all. So, which is why we switch to the Fisher divergence, which basically compares the gradients at each position. And this is something that you run into quite often if you do the normal KL divergence minimization, that that you end up with posterior approximations that are very much not smooth. So that is one of the failure cases where kind of this preconditioning doesn't work otherwise. So instead we use the Fisher divergence, just the norm of the gradients with some things. That is also the statistic I mentioned at the beginning for the practitioners that tells you how difficult is the posterior. We can also estimate it without a missing normalization constant. So we get an actual number that tells you how different is this. In our particular setting, that's not true in general, but in our setting, it's always true. The KL divergence is always smaller than the Fisher divergence. So if we get the Fisher divergence small, we automatically get the KL divergence small as well. So that's a natural consequence. It's a stricter way to measure the distance between the two. And this is what I now presented as NumPy's diagonal mass matrix adaptation. Now, a third change we want to make to things. What we really want from HMC is to fix up the posterior. We don't really want to sample the posterior, but we already think we've got a decent approximation. So, turns out we can use the information that we were fitting a normal distribution to the posterior a little bit to simplify HMC and really make it only do the work it needs to fix up the posterior, so that it gets really cheap if our approximation is good. So we just changed the leapfrog steps a little bit. Instead of going straight in the position steps, we go in an arc as we would go for a standard normal distribution. And that way, the integration error gets smaller as our posterior approaches a standard normal distribution, and then in the limit, we can make steps as large as we want with no integration error. So it gets cheaper and cheaper. We do that just by splitting the Hamiltonian a different way. Usually, we split it in kinetic velocity and kinetic energy and potential energy. Instead, we just split it into the Hamiltonian of a standard normal distribution and the residual term. And now something really nice pops out there as well. If you just look at that residual term, the flow generated by that residual term is exactly the Fisher divergence. So what we are actually saying, if we minimize the Fisher divergence, is make those adjustment steps, residual adjustment steps, small. Now, I would say this is kind of the framework that we can now build other things upon. So what's kind of stable in NumPy is the mean field version of that and a low-rank version of that. But now that opens up, I would say, kind of a whole field of what we can do now. We can pick and choose anything from the existing normalizing flow literature and just pop it in and see what happens. And that's kind of why it's experimental, because, well, we can do so many things, and it's hard to actually choose one of them. And it would be fun if other people play with this as well, I think. What I use mostly right now is are coupling flows, either real MVP style things, although I've made several over the time, several smaller changes to them. I don't think I have time to kind of go into them too much. But the basic idea of real MVP, or of a coupling layer, is that we split our variables in two groups. One group that we don't transform and one group that we do transform. And we use the unchanged variables to inform the transformation of the transformed ones. This is, funnily enough, a bit like a generalization of the Gauss elementary matrices in LU decomposition. So if you kind of a nonlinear version of that in a sense. And we just choose that split randomly and then flip it around and choose something randomly, flip it around and iterate that a couple of times. So for instance, on a 100-dimensional funnel, so just the standard Niels funnel, if you run that with diagonal mass matrix adaptation, we might spend 100,000 gradients kind of with default configurations and get it not to converge, so just less than 50 effective sample size of less than 50, so nothing essentially. If we fit this with normalizing flows, we spend less gradient evaluations and get good convergence on this particular thing. It takes, depending on your machine, because we need to optimize neural networks, it takes 5 minutes or something like that, 10 minutes. So why is this experimental? One reason, it's just this gigantic family of things that we can do if we want. But another one is kind of, sometimes it works and sometimes it doesn't. And for a long time that was quite puzzling to me, because sometimes you throw it on a difficult posterior and it works really nicely and perfect. Sometimes you throw it at something that looks really simple and also HMC might even deal with it and it just doesn't move much. It took me a while to understand a bit more about how that happens, and I think I'm getting to a point where I do. If I go back a little bit, here I said we split it randomly into those two groups, and that is a problem. Because the split really decides how well your normalizing flow works. And well, if you choose an integral part of your algorithm at random, then kind of how well it works turns out to be somewhat random, which is unsurprising if you look at it like that. But I think we have a lot of information that we could use to make this better. So from here, I would say there are really many ways forward of how to improve this. One way that I'm looking at right now a lot is to look at the Markov blanket structure of the model. So that's essentially the Hessian information where that structurally zero that tells you that variables are conditionally independent. You can pretty much use a lot of the literature on sparse linear algebra, just solving sparse systems, and a lot of that translates really nicely into the nonlinear case. So as I said, kind of the coupling flows are like elementary matrices, and the triangular flows or autoregressive flows, they work a lot like a Koleski decomposition. So there are many similarities there. One of the problems is, okay, how do we get the Markov blanket structure in the first place? In PyMC, I think I've now got a way to actually do that. In Stan, not so much. But I mean, we can always evaluate the Hessian if we want. Another thing that I think is a fruitful thing to look at is adding layers, not at the beginning, kind of not fixing your normalizing flow at the start, but just fitting with a simple one for a while, looking at the Fisher divergence or something else to see where we still have trouble, and then adding layers that target those problematic regions. There's also a version of that in NumPy already, but I'm not too happy with it kind of in detail. Another kind of completely different, or not completely, but different arc of work is to look at the model in detail and say, okay, for this particular model, I actually know what family of reparameterization makes sense. So kind of a very famous example of that is centering versus non-centering of variables. That gives you a family of reparameterizations. And we have ongoing work there together with Ricardo that looks pretty nice so far. So that gets me to the end, and I'd be curious to hear if you have, if we still have time for a little bit of questions. Yes. That'd be cool.
We have time for one normal question or two very short ones.
Thanks. A quick question about the architecture of your normalizing flows. So I assume you use a randomization or like a randomized split, a different randomized split for each different layer, yeah. Right?
I switched from randomized to something more systematic to make sure that each pair of variables gets separated at least once.
Okay, very cool. And how well does it work for very high dimensional posteriors? I assume the flow has the same dimensionality as the number of parameters, right?
So the way I parameterized it right now, the number of parameters is linear in the number of parameters. Yeah. The number of hyperparameters of the flow is linear in the number of parameters in the model. Too many parameters around. So kind of computationally it scales well. Higher dimensional posteriors have more freedom in how you can reparameterize them. So it does get more difficult, but it's kind of a bit of the same thing. Sometimes it works well even with high-dimensional posteriors, sometimes it really doesn't.
Yeah, because my worry is that like the coupling flows, because they have an invertible network, they don't scale so well, so very high-dimensional distributions. I don't know if it actually matters, because it's just for this preconditioning, so to speak. But this may be a challenge if you have like thousands of parameters.
Yeah, as I said, you can definitely run it with thousands of parameters. How well it works with thousands or 100,000s of parameters is a completely different question. Often it doesn't work too well, that's true. I'm really hoping that the sparsity information will help really, really a lot with that, though, because then the space gets much more smaller.
Very cool, thanks.
Okay, then I think, thank you again. Let's move on to Paul.